Already in terms of sine and cosine. None of my trigonometric identities have fourth powers in them. I don't have a rational expression to do anything with. I can only think of two possible things to try, and they would probably both work and lead to the same endpoint. One thing that helped me is to recognize that cosine to the fourth could be written as cosine squared. And then, like Tori said, you could either put 1 minus cosine squared in the place of the sine squared, or 1 minus sine squared in place of this cosine squared. Now, I don't remember why. Maybe I tried putting the 1 minus cosine square in there and it just seemed not to be going anywhere. I think it would. But what I ended up doing was putting 1 minus sine squared in place of the cosine squared. Oh, I know why. Oh, let me think what you're saying. I gotcha. Since you want to end up with a cosine squared, write this as cosine squared times cosine squared and only put this in place of one of them. Oh, I didn't think about that. That would work well. The way I'm going was okay. Now it makes me wonder if that would be faster. I'm going to try it. I'm going to put one of the cosine squares back in place of this guy. I can see where that's not going to achieve one thing I need. It's absolutely legal. This 1 minus sine squared is 1 minus sine squared times itself, and I'm just putting cosine squared in the place of one of the 1 minus sine squared. Is that what you were thinking too, Raven, or are you thinking something different? Oh, okay. Yep, and I think I ended up doing that a couple steps later. But to make sure that you have both sines and cosines in your answer, you can put 1 minus cosine square in place of that sine squared. I think I might have to stick with this so that when I FOIL it out, I have a sine to the fourth. I don't think this is going to get me a sine to the fourth. So nothing illegal about it. I'm just not sure it's a helpful move. So with my very neatest mark out, I'm going to FOIL this out. 1 minus 2 sine squared 2 theta plus sine to the fourth 2 theta. And this is a good place to do what Raven's saying, since I have to have sines and cosines in what I'm going for. I need to put a cosine back in there. And in place of that sine squared, I could put 1 minus cosine squared. All right. Double check me. Is that so far so good? There's my sine to the fourth. I'm going to try to leave it alone. What can I do after that? Any ideas? I'm thinking definitely leave this guy alone. Why not combine like terms? I don't see where that would take me, but seems like a useful thing to do in algebra. I'm thinking add this one plus that one is 2. And again, keep looking at what you're going for. You're going for a positive cosine squared. You have a negative cosine squared. If I just let me think about that. That could possibly be better than what I did. If you factored out a negative 1, you would have this one minus that one. No. This is where I have to write it down and look at it. But if you factored out a negative 1, you would still have minus negative 1. It would still be plus 1. All right. That seemed like a possibility. Okay. I think that's going to be it. Just don't worry about trying to see the end. Try something, combine like terms. Where did my minus cosine squared 2 theta go? Combine like terms and think somehow I have to get rid of these and get a positive cosine square in its place. I think all I'd have to do is replace this sine square with a 1 minus cosine square, and I bet everything would clean up right to what it needs to be. There's the 2 minus 2. It's going to allow me to get rid of the constants, plus 2 cosine squared. And when I combine like terms, I have exactly what I wanted. Uh, 14. Definitely more time and effort intensive than anything we did in 5.2. But it was pretty much just algebra. All right, you are ready for a new tool in your toolbox. And the way I had them numbered yesterday, this would be tool number 4, wouldn't it? You had 3 tools yesterday? This is the one that would not have occurred to me, I fear, if many years ago when I taught this for the first time, I hadn't looked at the solutions manual. I couldn't go anywhere with it, and I was just completely don't know what to do. And then when I got this tool, it fixed the problem immediately, and now I know when to use the tool. So it's whenever the denominator of one side is a binomial, and the numerator is a monomial, multiply by the conjugate. And since the only thing you can multiply by a fraction without changing it is 1, you have to multiply by the conjugate over itself, just like you do when you rationalize the denominator of a radical expression. Remember, if you have 1 over 2 plus square root of 3, and I say rationalize the denominator, what do you multiply by? 2 minus square root of 3 over itself. So this is the same idea, only because the original problem doesn't have a radical in it, it never would have occurred to me, oh, I'll just multiply by the conjugate. Look at number 16. I assumed that I would start with the left-hand side. I couldn't think of anything to do with it. I probably erased and then tried the right-hand side. I really just couldn't think of anything to try. But when I saw that other tool in the toolbox, it worked beautifully. Because what happens when you multiply by the conjugate of the denominator? Very often the denominator turns into one of your trigonometric identities. So multiply by cosecant y plus cotangent y over itself. This new numerator is exactly what you want to end up with. So you hope the denominator just is 1 somehow. And when you multiply these two denominators, you get cosecant squared. The outer and the inner cancel, and then minus cotangent squared. And that is one of your trigonometric identities. 1 plus cotangent squared equals cosecant squared. So if you just subtract cotangent squared from both sides, you have this, and you can put 1 in its place. So watch out for that. It's a nifty trick once you think of it. What about 18? Eeny, meeny, miny, mo. I'm just going to start with the left-hand side. What can you think of to try? Yeah, and believe it or not, that's actually not how I did this one. I don't know why, being as I had just done 16 by multiplying by the conjugate, but let's try it. I believe it'll work nicely. This is better than the way I did it. Then what? Here's one of my Pythagorean identities. If I get it in the form cosecant squared minus 1, which is this denominator, I can just put cotangent squared in its place. And the cotangent in the numerator cancels one of the cotangents in the denominator. That's much better than what I did. Number 20 is a bit different. Don't have a new tool. I don't think I'd want to multiply by the conjugate here, because if I did, I'd have a sine squared minus a tangent squared, and that's not one of my trigonometric identities. So that's not really going to help. I can see which side to start with, but then I'm going to need some help. Oh, right, the secant and the tangent in terms of sine and cosine. I don't see anything else to try. I think that's what we're going to have to do. Then what? Two things you can do, and it just depends on how you like to clean up your complex fractions. Some folks clean up their complex fractions by getting a common denominator, adding those two, getting a common denominator, adding those two, and then saying one fraction divided by the other is just one fraction times the reciprocal of the other. That's absolutely how some folks clean up their complex fractions. I think it's easier to multiply by cosine 4x over cosine 4x. You'll get the same thing either way. That numerator is cosine 4x plus 1. The denominator is sine 4x cosine 4x plus sine 4x. Any questions about that step? Then what? Yep. Who said that? Good job, Miss Kelsey. Factor out a sine 4x. It's your GCF in the denominator. Look at that. You have a whole cosine 4x plus 1 that will cancel. So if you did some calculus, whatever that is, and you came up with this answer, and you looked in the back of the book and they had this answer, my first instinct would be, I'm just way wrong. Those look so different, they can't possibly be the same. But then if you work on this a few more steps, sure enough, it equals that. So your answer's right. And on a calculus test, I would count this right, because I wouldn't expect it to occur to you that that could be simplified as much further as it can. But we're just talking about checking your answer in the back of the book, showing that your answer is equivalent to their answer. All right. Is there anything else new and exciting? 22 is kind of cool because you just have to stare at it until God speaks to you. Let's start with the 1 and see if we can expand it into the other side. Let's don't. Any ideas? Absolutely. That's exactly what it is. That's a perfect square trinomial, which results from squaring a binomial. Compare that to a to the fourth plus 2ab plus b to the fourth. That's just a squared plus b squared squared. Awesome. So we probably could do this by putting some 1 minus cosine squares in the place of sine squares or something like that. But if you recognize it as a perfect square trinomial and you factor it, look how awesome that is. Let's see. I want y'all to finish up the proofs this weekend. So I'm looking for anything that's different. Let me just put a few things up here. 28's not exciting because the trick there is just multiply by the conjugate of the denominator. 30 is interesting. Any ideas? We could engage in highly illegal canceling. The abbreviation is DOTS. No, it's not. It's DOTC. It's the difference of two cubes. That's where you get a binomial times a trinomial. See if you can factor that difference of two cubes. Somebody tell me what you got for the trinomial factor when you factored that. Plus, the last sign's always positive. Oops. A cubed minus B cubed is A minus B times A squared plus AB plus B squared. And then the cosine x minus x in the denominator cancels out that one in the numerator. And what else? These two guys give you 1. All right, I have one more that we definitely need to do. Oh, yes, sir.
Not necessarily. We not have sign.
You'd say commutative property of multiplication? Yeah. 32. Do you mean unfactor? Multiply. I don't see anything else to do. I mean, that seems like it's going to be a little bit ugly, but I don't see any way around multiplying this times itself and that times itself. See if you can do that. That's what I got from the first term. Wow. If you save your pre-calculus and your calculus notebooks and you look at them 20 years from now, it's fun. You look back at it and think, dang, I knew that when I was 19. I knew that when I was 20. And if you haven't used it since then, if you don't become a teacher or, some field where you're doing this, you'll look at it 20 years from now and not have any idea what it means. Just like, once I learned Chinese and then I forgot it. That's what it seems like. At least I have a pair of like terms that cancel, give me 0. I know, we're sick. Me too. This is what my brother and I do at New Year's Eve parties. Okay, then what? I think that's the key. Just figuring out how to group it for what I want to happen to happen. Do you have any ideas on how I should group that? I think you'd have to in order to have a GCF to factor out. You could group these two and factor out the A squared, but I like your way better.
Well, no, because then the sine squared is
Oh, okay. And then these and factor out. Oh, I do like that. It'll work either way. But if you factor the term, or not factor, but group the terms that have A squares, and group the terms that have B squares, you can factor in A square out of the first group, and you're left with a trig identity, or Pythagorean identity. And the second two, you're left with a trig identity.